These engineers wanted to build a communications satellite using low-budget, off-the-shelf technology. The type of devices that had never before been sent into space.
In the mid-'80s, everyone thought we were crazy to do this. The sort of mainstream industry say, why are you doing this? This is kind of like a toy spacecraft, because most spacecraft use special electronics to work in space.
Most satellites at this time were built to withstand large doses of radiation.
If we think back, the 80s was still the height of the Cold War. So many of our critical satellites were designed essentially to survive nuclear warfare. So they were really robust against radiation damage.
But with the team sending untested commercial technology into space, Craig's mission was a big risk at the time.
It carried some very early experiments in digital communications and digital imaging. In fact, it was a pioneer of these techniques. We were flying state-of-the-art technology, similar to the emerging personal computer technology at the time, devices that essentially have an unknown heritage in space. So part of the activity was to see exactly how do these things respond.
No one on the team knew how this untried technology would react in orbit. But the experiment so intrigued NASA that they agreed to launch the satellite for free. But only under the strict condition that it was ready to launch in just 6 months.
To get any satellite designed and built in this time is absolutely record. We're normally talking about years to design and build a spacecraft, and this was done remarkably quickly by the team.
We have ignition, and we have a liftoff.
When we launched the satellite, we got data back. It's always exciting the first time you hear your spacecraft.
To keep these highly sensitive computer chips running, the team installed software to immediately fix any memory failures.
We had what we call error detection and correction coding systems. So if there were any errors in the computer caused by radiation damage, these would be detected and automatically corrected. What we realized then is that we had a unique resource.
Each error message clearly recorded the exact position of the satellite when the failure occurred.
The chips we were flying turned out to be quite sensitive to this radiation, so we were getting a large number of errors. One thing I did was started to map out where these errors were occurring, and that gave me a view of the errors from the perspective of a map. That really then, in a very concrete way, showed you exactly what was going on. And to my surprise, really, we got an awful lot of errors just off the coast of Brazil in a region of the South Atlantic. This area of the South Atlantic was giving us errors all the time, every day, every time we passed through it.
Although unintentional, Craig had helped to create the most accurate map of the South Atlantic Anomaly to date. What John wants to find are artifacts that have gone through a very specific process. They must be heated to over 1,076 degrees Fahrenheit, then rapidly cooled. This process locks in the strength of the magnetic field at that particular point in time and location.
This is exactly the same type of information that is being recorded at a magnetic observatory. It's just like this is a spot reading of the magnetic field back in time. And we just need to find enough of these to string them together to get a magnetic history.
But where do you find rocks amongst this vast South African wilderness that have been heated in this very specific way? This is where John's archaeologists are key. Tom Huffman has dated the regular movements of human populations here across thousands of years.
This is a special place for Iron Age studies. That's the last 2,000 years. It's Black prehistory. This is a special place because we can do what's called landscape archaeology. We have data from tree rings, we have data from the isotopic study of bones, that we know that the climate has gone up and down. The climate alternated between not so good, really good, not so good, etc. And it so happens that there's a correlation between the increase in population by the number of sites of that time period with the higher rainfall periods and so on.
One of the tribes that migrated to this region regularly, called the Bantu, had some interesting cultural practices that offer John a unique resource for his study.
The Bantu were the first people practicing agriculture in this area. So they, of course, were very reliant on rainfall. And at times of low rainfall, times of drought, they had ritualistic burnings of the village.
By burning their settlements during a drought, the Bantu believed this would call on the rain gods and bring better weather. These regular burnings have left a series of rock samples providing a historical timeline.
The fact that there were several migrations of Bantu into this area is ideal, together with this ritualistic burning, because that actually created this time sequence.
Today, John and his team have found a new undisturbed area of burning, something that could give him crucial insight into what's driving the anomaly beneath Africa. First, John takes GPS readings to locate the precise position of the ancient sample.
The key thing now. Nice place here. Where we can get aid.
He then draws a line on the rock to provide a reference. Using compass readings, he specifically orientates the current magnetic field. Before taking the sample back to the lab to analyze its historic magnetic strength.
Every picture you see here on the wall, space radiation has impacted. Everybody here has flown in space, and they've all been irradiated in ways that just don't happen down here on Earth.
And there's a limit to what can be done to avoid many of these dangers.
If you're going into space, you can train, and you should train as hard as you possibly can and be prepared for as much as you possibly can. But at the end of the day, you're going into the unknown, and there is an element of unknown and an element of luck. The last problem that we had is not the one I worry about. I worry about the next one that we haven't had yet.
But with our appetite for space travel increasing by the day, the problems will continue well into the future.
In the short term, we're going to see a lot more photos on the wall somewhere of space tourists. We're going to be sending a lot of people into space for short duration missions. But for the longer duration missions that NASA's doing, that our international partners are doing, we're going to have to address radiation, especially as we go out beyond the Earth's magnetic field. Or if things like the South Atlantic Anomaly grow and make it more dangerous in low Earth orbit. Radiation is a big threat, and it's the #1 threat, in my view, to humans flying in space.
Around the corner from Frenchie's, Dr. Zarana Patel recreates these harmful space radiation environments in this facility at NASA, and can see exactly the impact the radiation has on the human body.
We are collecting blood samples from the astronauts before, sometimes during and then after their flight, and quantifying their DNA damage.
The damage caused by just a single particle of radiation can be lethal to body cells.
It is powered with enough velocity and enough energy to go straight through your DNA.
As a particle hits our DNA, it can rip apart the chromosomes and change their structure.
If you have a hit on your DNA, the body can repair, or it can also misrepair.
Our body naturally repairs DNA damage, but when the impact is severe, the repair mechanism can fail, And it's this process that Zorana is most interested in.
We've chosen 3 different colors, the red, the green, and the yellow, to highlight 3 different chromosomes. And you can see here a green that has misrepaired with the red here.
Individual chromosomes are colored with fluorescent dye, showing any that incorrectly combine with themselves or other chromosomes. And this can lead to irreversible damage.
So when you have misrepair like this, we won't know that it is repaired adequately, and if it isn't, then you will have long-term impacts and eventually cause initiation, progression of cancer.
Although a direct link with Terry's cancer can't be proven, in just 2 weeks in space, he experienced around the same radiation levels that most people in Houston receive in 6 years. As the South Atlantic Anomaly grows, so will the radiation exposure to astronauts. And with engineering yet to solve the problem, could biology provide the key to keeping them safe?
So what I am proposing may sound quite futuristic, but this technology can really help human beings in either space travel or here on Earth. Because humans, for the most part, have evolved in a pretty shielded environment where our planet's atmosphere was able to deflect a lot of the solar radiation and the cosmic rays that come from space, we have never really needed to evolve a way to protect ourselves from a lot of the space radiation that astronauts would experience.
Lisa's work involves studying animals that live in extreme environments here on Earth to see how they have adapted and evolved.
So there are many regions of Earth where humans could not possibly survive for any period of time. But still, in these environments, there are species that are able to tolerate these harsh environments, and what we call them are extremophiles.
These microscopic creatures have evolved to survive in some of the most extreme environments imaginable.
And by studying these extremophiles and really trying to understand how they survive these harsh conditions, we can better learn ways to protect ourselves in the future.
And there's one of these extremophiles in particular, called Deinococcus radiodurans, that Lisa thinks could play a vital part in the future of space travel.
And you can see here that there are streaks of this Deinococcus radiodurans. What is interesting about them is that they have some cell surface proteins that bind to an orange pigmented compound that is able to give some antioxidant properties. When these species are bombarded with radiation and it experiences shearing of its DNA, it's able to use these antioxidant properties to make really rapid and clean repairs to any damage that it has experienced.
Lisa's ambitious plan is to find the genes responsible for these rapid repair mechanisms and incorporate them into human DNA. By transferring this unique activity into astronaut body cells, they could be better able to repair DNA damage, making them effectively immune from the potential cancer-causing radiation in space.
If humans were able to perfect the ability to gene edit, we may be able to remove the costs of building the more physical aspects of space travel, like building protective shields or building aircraft. And if we were able to localize this kind of tolerance within ourselves, it may really accelerate the way that we can travel into space in the future.
Gene hacking humans to make them suitable for spaceflight could be centuries away. It may never happen. But the problems the South Atlantic Anomaly are causing aren't just going to affect astronauts now or in the future. Some scientists think the problem may one day affect the future of humanity here on Earth. The radiation above the Earth is driven by the changing activity of our sun.
We really start by trying to look at what the sun is doing, and that will give us some indication of what's likely to affect the space environment around Earth in the next minutes, hours, and days.
Dan and his team look for solar flares, super-energized radiation particles that are released from the sun and stream towards Earth.
Energetic particles from the sun can probably be thought of somewhat accurately as tiny but very powerful bullets that are being generated by the energy on the sun. Those powerful bullets, if they were to strike a spacecraft, they could cause damage within a spacecraft or within the electronics of a spacecraft.
But in fact, the Earth is incredibly well protected from these solar bullets by its remarkable magnetic field.
We have this wonderful protective umbrella above us. The Earth's magnetic field prevents much of the powerful energy from the sun.
This magnetic force field shields the Earth in two ways. It deflects some of the dangerous particles back into outer space, but also traps some radiation, holding it in a layer that comes as low as a few hundred kilometers above the Earth's surface.
So we have both the fact that the Earth's magnetic field, in a sense, prevents radiation from getting very close to the Earth, but it also provides a trap for particles to be embedded within the magnetic field for long periods of time.
Beneath this dangerous blanket of trapped radiation, the International Space Station and many of our key satellites fly in what is called the low Earth orbit. But this safe zone doesn't always provide the protection that scientists expect. That means any astronauts passing through this zone need to be monitored. And that's the job of Kerry Lee and his team.
We're in the multipurpose support room, which is a back room in mission control at the Johnson Space Center. And our goal here is to keep the astronauts protected from space radiation.
Valid until 09, huh?
Yep.
Okay. Thanks a lot. I appreciate it.
All right.
On board the space station, live radiation data is beamed back to Kerry. And it reveals what happens when the International Space Station flies over the South Atlantic.
You can see there are some irregularities that happen at various places within the low Earth orbit. We see 6 or 7 of these peaks each day.
These peaks in radiation occur each time the space station passes through the South Atlantic Anomaly.
When the International Space Station passes through this intense region, over here you can see individual frames and the intensity increases where you have more hits in the detector.
Over the South Atlantic, the trapped radiation that should be held safely above the Earth dips down into the low Earth orbit, creating this radiation hotspot, the South Atlantic Anomaly, much closer to Earth than expected.
Robin, how's it going?
It's good. Swipsy just called. We've got a KP of 5, and they hit a warning for a 6.
Okay.
Deep within NASA's Mission Control Center, a small team of scientists monitor unusual activity from space.
You ready to write the alert?
Yeah, I'll get it set so when we hit it, we can just send it out.
Okay, sounds good.
The team here work 24/7 on a complex mission to protect astronauts from the dangerous environment of space, something many have experienced firsthand.
Okay, Zambo, looks like the weather came together tonight. The vehicle's in great shape, so it's time to go fly.
5, we have to go from ready to start. 2, 1, 0. Booster ignition and liftoff of Shuttle Endeavour with NASA's final space station crew compartment that brings a bay window view to our celestial backyard.
We had launched early in the morning, about 4 a.m., very cold February, Florida morning in 2010.
For former fighter pilot Terry Virts, this was his first mission into space.
One of the most special experiences of my life was seeing Earth for the first time, because I launched at nighttime, and I had a chance very briefly for a few seconds to see the whole east coast of America. Kind of took my breath away. I wasn't prepared for that emotional impact.
Terry was one of 6 astronauts on a 14-day mission to finish constructing the International Space Station.
By our 5th day in space, we were docked with the space station. We were about 400 kilometers in altitude above the Earth. It was a normal day.
It may have been a normal day for someone trained to work hundreds of kilometers above Earth, but what happened next changed Terry's life forever.
I was exhausted like I was every night, getting ready for bed. I got on my sleeping bag, pulled it over my head, closed my eyes, and just a few minutes after that, I saw this giant white flash. And I opened my eyes, and my first thought was, what was that? Computers were fine. There was no problem on board. None of my other crewmates woke up and said, hey, did you see that? It was just me. And then it wasn't long after that, a few days after that, that I started noticing my face was bleeding. And I'd do this and there'd be blood on my finger. There's a lot of mystery in space. There's a lot of things that we don't know. It's the unknown for a reason.
Terry had just crossed into a region scientists call the South Atlantic Anomaly, the so-called Bermuda Triangle of space. It's an area of heightened radiation, which experts have been aware of since the dawn of the space age.